Hello, in this video I'm going to go through a few topics relating to polynomials. The first of which is going to follow some of the material from the textbook, which is on nested multiplication and synthetic division. And so I'm going to lead by an example. So we have this degree 4 polynomial 2x to the power of 4 minus 8x squared minus x plus 2. There's one thing to note here, aside from the fact that it's degree 4, there's no cubic term expressed. But that will become relevant in just a moment. So in terms of nested multiplication, this can be a computational efficiency. If you have the question, what is p of 2, then you might just go straight at it. 2 times 2 to the 4 minus 8 times 2 squared minus 2 plus 2. So you could evaluate this. And you might already see the result if you're thinking a little bit ahead. But if you don't want to do so many multiplications, so here in principle you have 2 times itself 5 times, here it's 8 times 2 times 2, and then add up all 4 numbers, you might essentially save some of the work. So essentially the powers of 2 that occur in the x powers, they only need to be calculated once per exponent. So the way that I'll think about this is to take the first 2 terms, the highest degree terms, and take the largest common factor of x. So here we have x to the 4, here we have x squared, so they have a common factor of x squared. So I can write that down, taking out the x squared, that will be left with a 2x squared, and then I'll be left with an 8, and all of that times x squared. Then the remainder of my polynomial is minus x plus 2. Now similarly, I just think of this as the coefficient of x squared. I have 2 terms, they have a common factor of x, and so I take that out. Now the first term will be whatever the coefficient was, so that's 2x squared minus 8. And here I have x squared, so after taking out one of the x's, I'll just have x. Here I'll just have minus 1 multiplied by x plus 2. So now if I want to evaluate what is p of 2, there's not much more that I can do in terms of this nesting. So inside here, this 2x squared minus 8 is nested inside the other bracket, which is why we're getting this nested term. There's not much that I can do here with this first, whatever that happens to be, times x plus 2. This is a constant. There's no common factor of any power of x. So in order to evaluate p of 2, I'll just work from the inside out. So at that point, this is going to be 2 times 2 times 2. So that will already be 8 minus 8. Conveniently, that's just going to give me 0. That will be multiplied by 2, although 0 times 2 won't be very interesting. Minus 1 times 2 plus 2. So I'm just substituting in the 2. So this already is 0. So that whole thing is 0. And so we just have minus 1 times 2, minus 2 plus 2. And the result gives me 0. One of the things we can do to save ourselves a lot of writing when we perform this type of nested operation is instead of using all these x to the power of whatever it happens to be, we use position to denote the exponent. So in this case, starting with the highest exponent and reading its coefficient, so the 2x to the 4, I just write down 2. Then the next position I consider the cubic term. There isn't any, so I'll consider 0. Then quadratic has a coefficient of minus 8, and the linear has a coefficient of minus 1. And finally the constant is 2. And so I'm not explicitly saying that this is degree 4, but that's implied by the position that I have everything in. So I know that the rightmost is going to be the constant, so going linear, quadratic, cubic, and degree 4. Okay, now to mimic the same thing that I was doing before, what we had was 2x squared, and I'm thinking x is equal to 2, evaluating what is p of 2. So I'll make a note that I want 2 here, and the approach that I'll take is simply add up the column. I get a 2, and then when I'm going diagonally upwards, I think of this as multiply by 2. Multiply by the value that I'm trying to evaluate at. So multiplying 2 by 2, I get 4. Adding the 0, we just get 4 plus 0 is 4. Multiplying by the 2, well, that's going to give me 8. And so at this stage in the calculation, I've said 2 times 2, and then that's, well, 2 times 2, and I've multiplied it by the 2 again. So what I've done here is already calculate the 2x squared. Now 8 that I have, minus 8. Adding up the column, I get 0. And so that's this 2x squared minus 8. And I have the result of 0, as I did before. Now I multiply that again by 2. So 0 times 2 is 0. That will give me this whole thing. Next I subtract 1, adding up this column, or essentially this part of the equation. So we get minus 1. We multiply that by 2 diagonally, so we get minus 2. And adding that up, we get 0, which is the ultimate 0 that we have here. So the first immediate result of this is that it's taken up a lot less space. I haven't had to do so many things in order to express it in this nested form to begin with, and I've also evaluated the result. I know that this value down here is p of 2. And if I did the same game with a different number, so if I wanted to take p of 1 or p of 7 or whatever I wanted, I would replace this by the 1 or the 7. And every step when I go diagonally, I would multiply by that number, still adding up the columns, but the diagonal is multiplying by whatever it is that I'm evaluating the polynomial at. Another feature that falls out for free is actually that p of x, the original polynomial, it has a factor of x minus 2, and I know that because p of 2 is equal to 0, but actually these numbers here are the coefficients of the other factor. And so the constant is minus 1, the linear term, well, there isn't one, it's 0, the quadratic has coefficient 4, and then the cubic has coefficient 2. And so this is going to be 2x cubed plus 4x squared plus 0 times x minus 1, and the remainder in some sense is 0, so that's the 0. So continuing with another step, I'm taking the cubic at this point. So that was 2x cubed, 4x squared, 0 times x minus 1. And I'm doing the same operation. So adding columns, I just have 2, multiplying across diagonally by this 2. So that'll be 4. Adding that gives me 8, 16. Just gives me 16 again. Multiplying by 2 is 32, and adding 31. And this will be the remainder in some sense. So similar to the previous case. So that tells me that x minus 2 is not a perfect factor of this cubic, that we have a remainder. So we can write p of x. We still have our x minus 2 from before. I'll just use square brackets to denote this a little bit more fully. So then we have our x minus 2. Then these coefficients give me a quadratic. I can tell that because I have 3 terms. So we get 8x plus 16. And then I have a remainder of 31. And so this gives me another expression for p of x. And I still also have a 0 if I want to have it there. I'll go one more step. That's to take this quadratic. So set up the same procedure. And now we have 2, 8, 16. And I have my 2 over here. So adding up the columns, multiplying by the 2. So we get 4. Add those up, we get 12. Multiply, we get 24. Add those up, we get 40. And so this is a type of remainder. And so what we have from this is that p of x can be written as my initial x minus 2, then the x minus 2 that I found in the previous, and now I'm looking at, I'll use a curly bracket, I'm looking at this quadratic, and so that had x minus 2 multiplied by 2x plus 12, plus the remainder, 40 in this case, and then I have to tidy everything back up. So that was my quadratic. Now kind of centered at x minus 2. So we had a plus 31, close my square bracket, and a plus 0. Now the next thing will be to work with this linear term, but actually I can work with this somewhat directly. In order to write this in terms of x minus 2, so I have a 2x should occur. So I need 2x, and I write it in terms of x minus 2. And then what's left over, I need my 12, but I'll get minus 4 from this, so I need to have 16. And so this expression here is equal to the 2x plus 12. And what you might recognize from this is it's again a nested product. But now instead of being a nested product in terms of x, it's a nested product in terms of x minus 2. If my problem that I'm looking at is somehow very much centered at the value x is equal to 2, then such a nested product is going to give me a good idea of how the function is behaving at that point. But actually in practice, the numbers that I'm looking at for the coefficients fall out a lot more quickly than writing everything out in long form of polynomials, but rather I can see it as the remainders for the different tables that I had. I'll leave it as an exercise to unravel the brackets above, including this piece inside of here, to write down p of x. This 2 will have x minus 2 to the power of 4. This 16 will have x minus 2 cubed. The 40 rather will be next. That will be with the quadratic. And now we'll have the 31. So essentially I'm going from inside to outside. That will be the linear. And then this 0, we know that p of x is divisible by x minus 2. So each of these will be 0 at 2, so we're left with p of 2. Synthetic division gives us a good approach when we want to divide a linear term into any polynomial. So we write down just the coefficients that appear in the polynomial in some table that we understand the meaning behind. And then we go through the algorithm and we interpret the result. This is relatively quick. If we want to do something a bit more general, so let me just give an example here for polynomial division. We can do this if we want to have a linear factor into any degree polynomial, but the synthetic division is going to be a lot more efficient. So when I talk about polynomial division, I probably mean long division only. So something where I'm dividing at least a polynomial of degree 2 into a higher degree polynomial. So for example here I will take x squared minus x plus 1, and then long division I'll divide that into x cubed plus 2x squared minus x plus 1. And so the route that we take with polynomial division is that we look at the highest degree term in each polynomial. So I'm dividing a polynomial with highest degree, the quadratic, so it's just x squared is the term, and then here dividing it into x cubed. So in order to make x squared match up with that x cubed, I multiply by x. Now the convention is to make a record of what you're doing, so I have an x up there. And then I multiply this x by the quadratic, the thing I'm dividing in, and so x times x squared, it will give me x cubed. Now by design, I'm making these the same. I'm choosing this x so that these two are the same. Then x multiplies the next, so that will be minus x squared. So we have minus x squared. And x multiplies the next, so it's just x. So we get a plus x. I then subtract this off. Usually it's good to bracket everything, subtract. A common error with this is to lose track of when you're subtracting something, and you disregard when you multiply this minus 1 in. So please keep track of this carefully. So x cubed minus x cubed will be 0. I won't bother write that down. 2x squared minus x squared together give me 3x squared. Minus x minus x, that will give me minus 2x. And there's a plus 1, but there's no constant down here, so it's just plus 1 or plus 1 minus 0 if I want. So then it's the same approach. I'm now dividing this x squared minus x plus 1, but looking at the x squared really, into this polynomial, and so looking at the 3x squared, and so I need to have a 3, because 3x squared is what I have down here. So 3 times x squared, I do the calculation again just to make sure, then minus 3x, and then 3 times 1 is 3, and then I subtract that off. What I get from here, 3x squared minus 3x squared, by design that cancels. Minus 2x minus 3x, so that in total will just give me an x, and then 1 minus 3, so we get minus 2. And so what that tells me is that the polynomial I started with, it's the cubic, that's equal to the polynomial I was dividing in, so that's multiplied by this x plus 3, and through the calculation I was multiplying by the x plus 3. Here is it multiplied by the x, subtracting off the original. Here is the quadratic multiplied by 3, subtracting off, again, the whole thing, the original minus each piece. So this is accounting for most of it, but then not everything. So we still have another part left over. This is the remainder, and so we will say plus x minus 2. And the algorithm isn't proceeding any further from here. Now this algorithm works quite well. It works for any type of division you want to do with polynomials. So regardless of what degree polynomial you're dividing into, or whatever degree this polynomial is, it all works. However, if you're dividing a linear term, then synthetic division is going to be a lot more straightforward, usually. Now to end, I want to make a brief mention on some topics relating to roots. And so if I take a polynomial, I'm just going to concentrate on its roots for the moment. So it might have some overall leading coefficient. But if I'm thinking of it as a cubic polynomial with 3, I can think of them just now as real roots. Later when we encounter complex numbers, you can even think about these as complex roots. So we're thinking it has 3 roots, a, b, c. If I multiply this out, then I'm going to have many terms. 2 terms in each of these brackets. So if you just expand the whole thing, you'll actually get 8 terms in total. But we know it's only a cubic, so in the end we expect to see only 4 terms, the cubic, quadratic, linear, and constant, because some of the coefficients will combine when you have the same power of x. So the result will look like something times x cubed, because we have 3 linear factors, plus something times, I'm leaving myself space, x squared, plus something times x, plus a constant. And it will always have this appearance. Now maybe some of these coefficients will end up being 0, but nevertheless it will always look like this. And so starting with the cubic, the only way I can get x cubed from this expression is if I take the term x from each of these factors. And so that's x times x times x. And so the coefficient here, I can think of it as just 1. Now if I want to take x squared, I have different ways of getting x squared. I could take x from the first vector, x from the second, so I have to take minus c. And precisely the ways are to take x from two of these factors and not the third. So for example, x from the second and third, but not from the first. So in that case, I'm going to have a minus c by taking this constant and the other two with x, a minus b by taking this as the constant and the other two with x, and a minus a. So what we'll actually get is minus a minus b minus c times x squared. Then if I look at the linear, so it's x, this is essentially take x from one of the brackets and then take the product of the other two constants. So that will get me something times x. Minus b times minus c, that will give me bc. Then if I take the x out of this one, I'll have minus a times minus c, so ac. And essentially it's just all ways of multiplying two of these together, two of these constants together. So that will give me ab, so taking the x from here, ac, taking the x from this bracket, and finally bc. Then the constant term, that can only happen if I take the product of all three of these, so minus a minus b times minus c, and so that will be minus abc. What I should point out here is that this is minus 1 times the three roots, the product of the three roots. This is the sum of all products of two roots. This is minus or minus 1 times the sum of all roots. And this, unimaginatively perhaps, is the number 1. And the pattern that's happening here is that you can read right to left or left to right. I'll take right to left here. These are alternating in sign because here I have an odd number of things. So we have minus 1 to the some odd number, 3 in this case. Here it's an even number, so it's minus 1 squared in that case. And here it's just minus 1. So we have this alternating sign happening, depending on how many factors we have. Otherwise, this is the product of all roots. This is the sum of all possible products of all but one root. This is the sum of all possible products of all but two roots. So by knowing what the roots are of the polynomial, I can work out the coefficients directly without having to go through calculating all 8 terms in the expression and then combining. We can use the roots to go essentially and just figure it out directly. Now I've simplified the problem here in 2 different ways. I've taken a polynomial which has leading coefficient 1, so I can just ignore it. That's why I'm getting a 1 down here. And I'm taking a very particular example, something of a cubic polynomial. However, the general statement about this product of all 3, product of all but 1, product of all but 2, product of all but 3 technically, and an empty product is just 1 by default. But for the general, please see page 106 in the textbook. And that talks about a general polynomial of degree n and how you calculate the different coefficients. That can sometimes be useful if you have limited information or you only want to determine limited information. And it will come back up again when we talk about complex numbers and understanding how we solve polynomials with complex numbers.